soon.
So we're very fortunate to have Alan Ritter visiting us here. I've known Alan for a long time. We were both grad students with Oren at UW. Early in his career, Alan did a bunch of exciting work with Twitter data, was the leader in that space, and since then has done a whole bunch of exciting things in NLP, including some work with scientific documents. So it's great to have him chatting with a bunch of us on Semantic Scholar today. And he's going to talk to us about efficient use of pre-trained models. Take it away.
Great. Yeah. Thanks so much for the introduction, and thank you for having me to speak. So I think we all kind of know about this issue that like things are just getting expensive to kind of run NLP experiments or build NLP models, right? So just to give sort of a concrete kind of example of that. So if you kind of if you wanted to get a rough estimate of like what is sort of the total cost of ownership of like a high-end GPU server, like an 8 AWS, 8 A100 GPU server on AWS, it's like, to kind of get a reserved instance that has this for a year would be something like $140,000, right? So this is actually quite a bit of money. And so if you're like a company, you might be kind of in this situation where you're trying to decide, okay, should I like hire another employee or should I purchase a GPU server? And I don't think we have like a very good way to think about how to make these type of decisions. And so of course there's other kinds of like negative externalities involved in this as well. So, like carbon emissions. So, kind of running this server, at half capacity for a year is kind of roughly equivalent to driving like a standard internal combustion engine car around for a year, right? So there's, some kind of important kind of considerations here. But there's also like other kinds of costs associated with training these models. So there's also some sort of like human annotation costs. And so this is just an example from the original Instruct GPT paper. And you can see kind of the first step of training these sort of instruction-based models is to hire contract workers to basically label demonstrations of the outputs for a bunch of kind of user input prompts, right? And then of course these would then be used to fine-tune GPT-3, which costs a lot of money to pre-train. And so I'm not actually going to talk about instruction fine-tuning in this talk today, but I just wanted to kind of use this as an example of this kind of trade-off between computational costs versus human annotation costs, right? And basically the idea here is there's some sort of, how should we kind of spend money on these sort of two different types of costs, and how should we kind of balance these is really kind of the question. And I think this comes up in a lot of different situations other than just kind of instruction fine-tuning. So there's sort of two different kind of scenarios that I'm going to talk about where this kind of trade-off between computation and human annotation, we've done some analysis on. And so the first one is in the context of domain adaptive pre-training, which is something that people here have worked on, of course. And so here we're looking at, if you have some NLP model and you want to adapt it to a new domain, there's sort of two ways you could think about doing that. One would be to do kind of pre-training on data from the domain, whereas the other alternative would be to sort of annotate supervised data for fine-tuning, right? So that would be like one place where this trade-off comes up that I'll talk about first. And then I'll also mention some more recent work that we just presented at ACL on the same type of trade-off in the context of knowledge distillation. Okay, so this is sort of the setup for the first place where we looked at this trade-off. So basically the idea here is we have some existing NLP model that's been fine-tuned on a data set for an existing task. And then we want to now kind of adapt it to work in a new domain, for example, like chemistry literature, right? And so I think there's sort of two different ways you could think about doing this. And both of these are definitely going to kind of improve the performance on this target domain. So one would be to simply hire annotators to label data for you in the target domain to use for supervised fine-tuning, and then just use sort of an existing off-the-shelf model to fine-tune with. Whereas the other alternative would be to pre-train an in-domain model for that target domain specifically, and then use the existing fine-tuning data from a different domain for fine-tuning, right? So these are kind of like two different alternatives. And so this was actually kind of a situation that we were in. We had this kind of new DARPA project to collaborate with chemists. to build kind of NLP models to read the literature and help them kind of design new synthetic routes. And at least for me, it was sort of unclear, like what was the best approach to begin with, right? Should we do sort of, should we just hire annotators to label data, or should we kind of pre-train these in-domain models? And so at the time, at least, I think it's fair to say that the conventional wisdom was that, labeling data is expensive. So you're sort of much better off just kind of making use of lots of unlabeled data in the target domain to kind of adapt models. But of course, now that, these, pre-training is getting sort of increasingly expensive in terms of computational resources, this sort of calls this assumption into question, right? Okay, so how can we sort of frame this question a little bit more kind of specifically so we can kind of, do some experiments to help some, make recommendations about how to make sort of good decisions about when to kind of, do domain adaptive pre-training versus in-domain annotation, right? And so kind of the key idea here is to borrow some ideas from, consumer theory, which is kind of like a subfield of microeconomics. So if you open up like an introductory microeconomics textbook, you might see like a figure that looks something sort of like this, where on the x-axis you have like the number of pre-training hours that you kind of trained the model for. And then on the y-axis is the amount of in-domain documents that you've sort of annotated. And then you can think of like any particular point in this graph is like a particular combination of pre-training and annotation that has some sort of cost associated with it, right? And so basically what we want to do is we want to pick a point that kind of falls under this black line here, which is like a budget constraint. So we have some fixed budget, right? And we basically want to pick the point that has the highest utility or, just F1 score on held out test data that kind of fits within the budget constraint. So that's kind of the problem setup here. And this is, basically just what I just said. Okay, so now we've kind of framed this in kind of a very precise way that we can kind of do experiments to kind of answer this question. There's just a few kind of remaining things we need to be able to figure out, like how much does it cost to label data? How much does it cost to pre-train these models and so on? And so, the first question is easy. So we've sort of annotated a bunch of different data sets ourselves so we can use these to kind of do experiments. We know how much the labels cost to generate. So these are like the different data sets that we're working with, or the different domains. So the first are this wet lab protocols data set we built. And so wet lab protocols you can think of as basically sort of like cooking recipes for how you would carry out like a biology experiment in a wet lab. And so these have these kind of relatively short sentences. They're relatively kind of direct and to the point about kind of the steps you should do to carry out the experiments. We also collected some paragraphs describing experimental procedures from PubMed articles as well. And these have like a more kind of academic writing style. And then we also have a data set of synthetic procedures collected from patents. These are basically like, how would you synthesize a particular compound? And for each of these, we basically annotated them with, a bunch of sort of entities and relations. It's basically, you can see what the annotations look like. And then we have kind of the estimate of like the price per sentence to annotate for each of these different domains. Right? Okay, so you might be wondering, like, okay, why are we so interested in these scientific procedures? And so this is basically this kind of DARPA project I had mentioned earlier, where we're collaborating with some chemists who are building robotic chemistry labs to kind of automate the synthesis of various different compounds to try to speed up this design, make, test cycle of like designing new molecules for like new drugs and things like that. And so by extracting information from the literature, this is actually really useful for them because they can kind of help to kind of like optimize reactions or come up with like, for particular reagents they're using, like what type of solvents should they be using, or like what temperature should the reaction run at, and things like this, right? Okay. So, so anyway, so that's the data that we're working with. I'm sort of skipping over some details about the, cost of pre-training and things like that, but that's easy to measure. So this is kind of what the setup looks like for the experiments. So basically, we'll start out with some fixed budget. So in this case, like $1,500, right, to train a model to kind of adapt to like chemistry information extraction. And so the first thing we'll do is we'll kind of allocate like a portion of that budget to do sort of in-domain pre-training. So in this case, we're starting with a Roberta checkpoint and then sort of doing continued pre-training on this sort of chemistry domain. And so that costs $800. And then, whatever budget we have left over after that, we can then sort of allocate to annotating these sort of in-domain chemistry documents with the annotations for fine-tuning, right? And so this particular combination then would correspond to like 1 point on this budget constraint that we can then evaluate by fine-tuning the model on the annotated documents and then basically evaluating performance on them. Okay, and so here's kind of the main takeaway results. There's a lot more experiments in the paper, of course, but these are basically like Pareto curves. So there's kind of 2 strategies that we're comparing here. And so, yeah, so on the x-axis is basically just as we increase the budget constraint, and then the y-axis is utility or F1 score. And so the gold curve here is basically the strategy where we just take the entire budget and just allocate it all into in-domain annotation, and then fine-tune an off-the-shelf existing model like BERT large in this case is where it is. Whereas the black curve is the strategy where we first pre-train an in-domain model. So we pre-train like a BERT-based size model on data from this kind of chemistry domain. And you can see that has a cost of about $600. And then whatever budget we have left over after that, we're just sort of investing that into in-domain annotation, right? And so you can see there's like this sort of crossover point where, if you have like a budget smaller than say like $1,000, you're better off basically just investing that all in annotation and not doing any in-domain pre-training. But once the budget gets kind of larger than that, you want to really do both, like both in-domain annotation and in-domain pre-training is like the more economical choice in that case. However, if you have to choose between one of these, if you can only do one or the other, in-domain annotation seems to be much more important than in-domain pre-training. Okay. So now we kind of have these, really good models for processing these sort of chemical synthesis procedures that are kind of pre-trained in domain. They're also fine-tuned in domain. So what can we actually do with that? So to kind of show like an application of this is a demo we built where we're kind of doing search over synthetic protocols. So basically what we did is we gathered about 6 million of these synthetic procedures. This is just an example of what they look like from US and European patents. And then we run all of our NLP tools over them, and then basically index the resulting annotations using Odinson. It's sort of like a search engine over NLP annotations. And then this would allow chemists to issue structured sort of SQL-like queries over this data to answer questions that would be helpful to them.
And I'm sorry.
Yeah.
A synthetic procedure means it's a procedure extracted from a patent that's doing some sort of chemical synthesis.
Exactly. Yeah. Yeah. You can think of each paragraph as kind of describing a chemical reaction, and then.
Okay, so it's not a synthetic data.
Yeah. Right. Yeah.
Data, real data about a synthetic procedure synthesis procedure. Just wanted to be clear about it.
Yeah, that's a good point, actually. Thanks. Yeah. And so this is sort of actually what we're doing here is kind of similar to this spike chord system that you guys obviously have, except we're sort of doing it specifically on these sort of chemical synthesis procedures in patents, kind of, doing it specifically for that. Okay, and so here's a just sort of a screenshot of what the interface for this demo looks like. There's also like a live URL if you're interested to play around with it, and a demo paper, and there's code and everything for this available. So this is just sort of an example. This is a question that we got from our chemistry collaborators. This was something they were actually interested to know, that they found that existing chemistry databases didn't really have very good answers to this question, which is, what solvents are typically used in reactions containing the reagent triphosgene, right? And so we can answer that here. This is basically just like a SQL query. We just type, triphosgene in the reagent slot and put like a question mark in the solvent slot. And you can see that we get back a list of about 60 different solvents. And this is actually quite a bit more than what Reaxys would give for an answer to this question. So Reaxys is like a commercial chemistry database. I think it doesn't have as good of coverage of like experimental details like this, which is why, by extracting information from kind of patents or the literature, I think we can kind of, supplement it and kind of get sort of more answers that would be sort of, helpful for chemists, right? So I think Reaxys is kind of like mostly hand curated instead of like automatically extracted.
And sorry, what's the chloroform?
Oh, yeah. So this is, that's a great question. I think these would be basically, so each one of these I think is representing like an individual, yeah, I would have to go back and look at this. Actually, that's a good question. I'm trying to remember. Yeah, I think this is just sort of like, so like these would be kind of like all of the reagents that appeared maybe in this particular, in these particular paragraphs. Like you could sort of click on this to drill down, And so I think these would be just sort of like other kind of mentions of the same thing here. Yeah, I'd have to go back and double check that. But yeah, I think we can make some sort of interface improvements here, right? This is like just like one of my PhD students' fan was kind of the one building this. But yeah, that's a good question. But yeah, I can't remember exactly off the top of my head. But I think it's just like, just different kind of, kind of mentions that were sort of clustered together somehow. But yeah.
Okay, thanks.
Okay, so anyways, and so just to provide some sort of anecdotal evidence that this is actually kind of a useful tool for chemists to use, this is like a tweet from our collaborator, Peter, who mentions that his whole group is kind of using this tool now. So yeah. Okay, so yeah, so coming back to this question of sort of like computational costs versus annotation costs. So I just finished talking about this kind of question, in the context of domain adaptation, where you're sort of comparing domain adaptive pre-training versus in-domain annotation. And so this is kind of some more recent work from my PhD student, Junmo, who is looking at this, similar kind of trade-off in the context of knowledge distillation, right? And so this is kind of the setup here, is you basically want to train a small model that will support efficient inference. And there's sort of two ways you could think about doing this. And so we're not doing domain adaptation here. We're sort of assuming we have some existing model and we want to sort of improve the performance on this target domain. So one way you could do that would be to simply kind of like annotate more data and then fine tune on additional data for this, this existing model. Whereas the alternative here would be to say, instead you could spend that budget on compute and just first pre-train a much larger model and then kind of distill the larger model to get like an efficient kind of a model that supports efficient inference at that end. So yeah, this is, I guess, what I just said. So let's say we want to, fine tune like a T5 small model here. And the first option would just be annotate more data. And then the second option would be to say like, fine tune T5 XXL and then distill it to get this compact model. Okay, so here are these same type of Pareto curves for the kind of knowledge distillation scenario. So there's sort of three strategies being compared here. So the orange circles here are basically the approach where you're not doing any distillation and you just invest the entire budget into data annotation. And you can see like how that improves as you kind of increase the budget. The blue squares are where you would, distill, basically first fine tune a T5 11 billion model and then distill it using 10,000 unlabeled examples. And then the purple stars are basically the same thing, except you're distilling using more unlabeled data. So it has like a higher computational cost, right? So this is basically, as you sort of go up here, you're kind of like allocating more of the budget towards computation and less towards annotation, right? So in this case, we see actually kind of the opposite trend where it seems to be sort of more economical to kind of invest in computation instead of annotation. Of course, you need some amount of annotated data to start out with to make this work. And so, yeah, we saw this similar kind of trend across like multiple different data sets and tasks. So yeah, it seems to be that kind of knowledge distillation is actually kind of a kind of more economical approach than just investing your entire budget into annotation.
Quick question. This is a T5 model, that the pre-trained T5 model, so it has the
Yes, that's right.
training to start.
Yeah.
Starting from scratch.
Yeah, we're not taking the pre-training costs into account. We're just only looking at like the cost of distillation, right? So it's like, should you just kind of like fine tune the smaller model, or should you, first fine tune a much larger model and then spend, like the fine tuning part actually doesn't cost that much. It's more about the kind of knowledge distillation as the more sort of computationally intensive part of this whole process, right?
So, do you get a bigger delta if you distill from an even bigger model?
That's a good question. So in the paper, we had different experiments with different size models of T5. So I think T5 11 billion this is kind of like the biggest gap, right? So this is from T5 11 billion to T5 small. I think you see similar effects with like different sort of combinations of like this bigger, slightly smaller source and slightly larger target models. But yeah, I think you will see like a bigger delta with a bigger difference between the large and small model. Yeah, I think you're right. Yeah.
Is there a way, so like, if I had this curve, I can make these decisions, but is there a way to sort of do this incrementally? Like say, like, I don't quite know how much budget, a little bit of a flexible, most things are a little bit flexible.
Yeah.
I want to slowly accumulate.
So is there some sort of like a scaling law or something like that? I guess you're thinking. Yeah. No, that's a good question. Yeah, we haven't like tried to come up with something like that. I think it may be relatively kind of model and data set specific, But yeah, I think it would be interesting to try to come up with some sort of more kind of, sort of a equation to kind of tell you what you should do, right?
Yeah.
Yeah, I mean, I think like just kind of the general recommendations, I think would be like something like, it seems like if you have more than $1,000, at least it's worth spending on sort of computation in this case, right?
Mhm.
I think that's sort of similar to kind of the findings we had for the domain adaptation setting, right? It's just kind of a rough general rule is like, maybe that's the point we're kind of investing in sort of pre-training or distillation makes sense. But yeah, I think it is really kind of model and data set specific. So yeah, it's a good question. Okay, and so yeah, we also looked at this kind of question of using GPT 3.5 as an annotator. So this was before GPT-4 came out that we did these experiments, but there was some previous work sort of showing that this can actually be like a more cost effective than using like say crowd workers on Amazon Mechanical Turk. And we basically sort of like, replicated this result, right? So you can see, GPT 3.5 seems to be a little bit more economical than using the human annotators in this case. However, it seems like if you actually have some data that's already annotated to begin with that you can use for fine tuning, it looks like it's actually better to kind of first fine tune T5 XXL and then distill that rather than using sort of, in context learning or few shot with GPT 3.5, at least for the tasks that we're looking at here.
So can you go back?
Yeah.
Right. Maybe you're getting to this, but you started out with this, let's try to find the optimal mix, but now it's just like we tried this, and this one seems best, but it's not any declaration of optimality.
Mm-hmm.
Is there an optimal combination or?
Yeah, I think it's, like I mentioned, I think it's sort of problem and data set specific, I think there are, like, at least from the experiments we've done, I guess maybe you could do a lot more experiments and try to come up with some sort of an equation or a machine learning model to try to predict, when is what is the right combination of, computation and annotation for this particular scenario. I think that would be like an interesting thing to look at for future work. Like we haven't done that, yeah, it's a good question.
Just to be clear, you first fine-tune T5 XXL on the data.
Yeah.
And it learns some function. And then this is the exact same amount of data you would have used to fine-tune the small model. but it's just easier for it to learn from a teacher than from the data directly? That's the finding?
No, so I think, so with the T5XXL distillation, you would be sort of allocating more of your budget towards computation than if you just kind of, so there's different, for each of these numbers here, there's like different amounts of data, basically, right?
Okay.
So for the kind of human annotation strategy, you'd be just investing the entire budget into human annotation. Whereas with the distillation, there's some portion of that budget you would have to kind of first spend on computation to actually do the distillation, right?
Yeah.
And then there's some budget left over after that you could use to fine tune, to basically annotate for fine tuning.
Right. And you didn't try the scenario I mentioned where you just use T5 as a weird intermediary?
Yeah, I think we did have experiments like that, because you could say like, maybe because you have all this unlabeled data, there's some sort of semi-supervised learning going on or something like this. I think we did do that experiment in the paper. I think that doesn't explain the difference.
Okay.
If that makes sense.
Yeah, thanks.
Okay. So, yeah, so this is kind of what I've talked about so far, is just this kind of general trade-off between computation and annotation. We did some sort of experiments to analyze this in these kind of two different settings. So the first is like this kind of trade-off between domain adaptive pre-training and annotating in domain, where it seems like annotation is kind of much more important in this case. And then in the second case, we looked at the same kind of trade-off for knowledge distillation, where it seemed like actually, fine-tuning a much larger model and then distilling it is actually kind of a good use of resources in terms of the computation that you spend on that. So the next kind of topic I wanted to kind of move to is some kind of more recent work that we've been doing on information extraction from tables. So we're basically trying to do this in a more sort of cost-effective way using large language models and kind of reducing the cost of annotation here. Okay, and so yeah, I'm assuming you guys all know about this kind of table extraction problem. There's a lot of previous work. So like this Axel paper is doing extraction from machine learning tables. There's also work on extracting, physical properties of chemical compounds from, material science and chemistry papers. And then, of course, there's a lot of work on extracting data from tables on the web as well, right? And so kind of the point that I wanted to make here is that, each one of these different domains or like different data formats, like, LaTeX or HTML or things like that, they all have kind of like separate sort of custom models that people are building. So these are just some examples of like the kind of main figure from a couple of these papers, right? So you can see they've kind of built this sort of, very complicated customized model to extract, leaderboards from machine learning papers or, chemical, physical properties from, papers on material science. And they also typically use, labeled data for each one of these domains, right? So it's kind of very sort of domain specific. And so I think this kind of raises an interesting question is, can we somehow kind of just have like one model we can apply to like all these different domains and data formats that can kind of, reduce the costs of kind of extracting data from all these different types of tables, right? Okay, so to do that, we're proposing this approach, which we're calling schema-driven information extraction. And so the idea here is you have, some tables, that you've collected in a specific domain. So in this case, these are like machine learning results tables. And then you have a domain expert who provides basically a database schema for like the format of the output that they would want from these tables, right? And this is like the only supervision that's provided to the model is a schema, basically. And then given, this schema, the task is to basically produce, a sequence of JSON objects, each one that has sort of like all the attributes, coming from the schema that's sort of describing the data in the table. And so there's going to be one JSON object for each cell in the table. So for example, here you can see, for this cell, this number like 345 million, there's a JSON object and it's sort of indicating, okay, this is a type of hyperparameter. The model that it's describing is Megatron GPT. and it has the name of the parameters, like the number of parameters in that model, right? And then, just this would be like another example is like this cell 0.755. We can see that's a, machine learning, the result of a machine learning experiment. The data set that it's on is SGD or schema guided dialogue. And, the task is intent classification. The evaluation metric is accuracy and so on, right? So this is kind of the task, right? It's basically just given a schema, can you sort of read in the table and produce this JSON output? Okay, so to kind of test the ability of current language models to be able to do this task, we built this benchmark of tables in 4 different domains. So the first is machine learning tables. So these are basically in a LaTeX format. We also have tables from chemistry papers on PubMed. These have sort of an XML format. We have some material science papers and also web pages. And so 2 of these are sort of like new data sets where we've annotated that JSON output ourselves. So we have something we can sort of compare the model's output to and evaluate how good of a job it's doing. And then we're also kind of repurposing 2 existing data sets as well. So it's a pretty diverse set of different domains and also data formats to kind of test how well these models can kind of generalize across different types of data. Okay, so one kind of challenge that we ran into, if you just sort of give a model this sort of table and ask it to produce that JSON output, is that the models tend to actually be a little bit disorganized in how they sort of go about extracting these JSON records. So just to kind of illustrate that, here you can see, if you give it this table as input in this particular example, what it'll do is it'll sort of first start by generating, JSON objects across the first row of the table, which is, great. But then once it gets here, it starts to kind of go down the first column, right? And so you can just imagine this is like not a very sort of organized way to extract the information from the table, and it's basically going to lead to kind of incomplete information. Like it's not going to be able to get all of the cells in the table. And so basically what we do here is pretty simple. We simply have some sort of rules to kind of have this sort of canonical order of the cells in the table, so we can kind of detect when the model has kind of gone off track, and basically truncate the output like after it started sort of extracting from the wrong cell, and then we basically just give it the value of the next cell that we want it to extract from as input, and then re-prompt the model with this new kind of input, which almost acts sort of like an in-context demonstration, right? And we found this is actually a pretty efficient way to extract data from the table. So on average, I think there was only about 3 times we needed to kind of re-prompt the model for each table. We do it in this way.
But this requires knowing the gold output, is that right? You have to.
So it requires knowing the values of the numeric cells in the table. So that's actually pretty easy to get just with some sort of just very simple parsing of the table, And the order is basically just like in the kind of LaTeX source code. This kind of left to right order is basically just starting from the beginning of the source code to the bottom, essentially. So it's actually pretty easy to kind of keep track of this canonical order and just kind of make sure the extractor sort of follows that.
Got it.
Okay, and so here's the results. You can see the blue bars here are basically the models using this schema-driven information extraction approach that I described. So instruct-T is sort of the kind of approach that we're talking about. You can see we also compared to a couple of open source models like StarCoder and Alpaca and FLAN-T5. So instruct-T is actually using Code DaVinci here. We're kind of currently in the process of redoing experiments with GPT-4 because this is sort of like a depreciated model. Yeah, it seems to actually work surprisingly well, and it's like on par with previous state-of-the-art results and supervised fine-tuning results on our this is on our benchmark, of course. Yeah, I think the really impressive thing here is this works without any sort of custom extraction pipelines. It works on a lot of different data formats and domains. And yeah, the only human supervision here is that extraction schema that you give as input to them.
how did the reprompting with the chat model?
Yeah, I think we may need to kind of adjust the prompts a little bit with the chat model. I think that's a good point.
Because you can't recontinue
Yeah.
at any arbitrary point.
Yeah. So it does work like using the same set of prompts. So I think we were getting about similar performance with GPT-4 to Code DaVinci, but we're kind of expecting, I think in most cases, you would see GPT-4 working significantly better than Code DaVinci, right?
You don't need a trick to
Yeah,
we starts.
Yeah, I think the chat models generally need like really slightly different prompts than the kind of ones that are not trained for chat. Yeah, so that's a good question. Yeah.
Is there a way to be like if I'm wondering how much of the like imbuing the model with schema and reading order and others would work for like Llama or these other models that we could run?
Yeah, that's a good question. Yeah, I think we probably should add some experiments with Llama. This is sort of work in progress. So this was, I don't know, somehow we just found that these sort of code trained models seem to be doing pretty well. So that's why we kind of focused on like star coder. Yeah, I think, doing this with Llama 2. Again, so at the time we were sort of running these experiments was before Llama 2 came out. So I think we may need to add that.
Or even with star coder, like is there like in terms of like the corrections and the extra information that's helping correct things from GPT, would it also boost star coder and these other models?
Yeah. So we're doing that same sort of error recovery strategy with star coder.
Okay.
Yeah. So it's a little bit frustrating, I guess, that the OpenAI models are working so much better than the open source models for this task. Like we spent kind of a lot of time trying to get the open source models to work better. I don't know. Yeah, maybe they just need some sort of, instruction tuning specifically for this task using like self-instruct or something like that. We're kind of thinking about ways to do that, but
You can just train a third of the data set, right, that you have to fine tune.
yeah, so that's what these sort of the gold bars are, basically where we fine tune on part of the data set. So like with T5, that can work sort of close to as well, I guess. So these are like not, the new data sets we've annotated are not like super huge. So we mostly annotated them to be just sort of like a test set, if that makes sense. But yeah, the supervised baselines for these other data sets, I think, are more competitive. So, yeah.
You only had 4 and 6 types of cells, I remember, for the ML and chemistry.
Yeah.
Thinking back to reading ML papers, there's way more types of cells. Do you just have large conglomerate taxonomies, or you discard a lot of cell and table types?
Yeah, that's a good question. So yeah, my PhD student Fan annotated some of this data and he did some analysis. I think he was finding that like for ML papers, like I think he had like one type that was like other or something like that. But just if you look at kind of the distribution, I think like most of them are result cells. There's some kind of like cells describing data sets and things like that. Yeah, I mean, maybe you could have like a more fine-grained taxonomy, kind of just break these down into kind of smaller categories, But I don't know, we just have like our, we had to design some sort of annotation guideline or sort of, that's a good question.
I guess we're very simple-minded people.
Yeah.
Do you know how critical it is to give the extraction schema, or could models induce that?
Yeah, I did have, well, we haven't tried to really get them to figure it out themselves. I do have sort of a backup slide. We did some ablations here, so you can see the result of like, we include like retrieved paragraphs of text, right? So like often the information you want to extract is not actually in the table, but it's in like the text or the caption or something like that. Yeah, the extraction schema seems to be pretty crucial here. So if you remove that, it doesn't really work very well. But yeah, we didn't try this thing where you sort of first get the model to predict the schema and then do the extraction, right? But I think even in that case, the schema it generates might differ from the one that we sort of annotated in the gold data, you know what I mean?
Right, when it gets this really low F1, is it actually a bad extraction, or is it just mismatched to the gold?
That would be a good question. Yeah, I think we may have to like dig into the data a little bit more to answer that. Yeah, I don't know the answer off the top of my head. Okay, And so then we also did evaluate on a downstream task, which is like this ML leaderboards task. And this does require a little bit more sort of post-processing. So it needs this kind of linking step. Yeah, I think you guys have some work doing that, right? Where you're sort of like, well, the schema-driven, i.e. we're only extracting like strings describing like an evaluation metric, for example, right? So to do the full task, you need to actually like link that to an ontology to kind of know that like two tables are talking about the same eval metric and things, right? So yeah, basically what we did there was we just replaced the relation extraction components and the Accel system with this table-driven extraction that I had mentioned, and then use their code for linking and classifying the tables and everything like that. And when we do that, we get performance that's basically on par with the original Accel paper. So I think this is, seems to indicate this is actually working pretty well, and has the potential to kind of dramatically reduce the costs of information extraction from scientific literature. Okay, so yeah, so finally there was just one kind of recent paper in progress I just wanted to talk about since it's kind of new, and I'm kind of excited about it. So this is some work by my PhD student Yang Chen together with Ethan Mendez, who's a Georgia Tech BS/MS student. And we're collaborating here with Shavik Das, who's a security privacy researcher at Carnegie Mellon. And so, yeah, so in addition to kind of like creating all these opportunities for sort of accelerating science and stuff like that, large language models also have some sort of new kind of challenges, right? So like, like challenges around sort of privacy and sort of personal information. So if you look, for example, at this new GPT-4 vision model, you can sort of give it, photos and then ask, any question you want. So you could ask it to kind of geolocate this photo, in which case it will, I think, appropriately, refuse to do that, right? Because, this might have been something posted on social media. The person sharing the photo might not have realized they're revealing their location. But, if you sort of just reword the question a little bit, it's actually not that hard to get it to actually kind of identify the location of the photo, right? And so I think it's actually a little bit unclear to some extent, like what is the right thing that should be done here. It's kind of like application specific and sort of like context dependent, right? So like if you're asking questions about like historical photos, maybe that's okay to actually kind of answer these type of geolocation questions about some, old historic photos. Where if it's a photo that someone shared on social media, then you definitely shouldn't, geolocate it, right? So basically the idea here is we're kind of, think that there should be some more kind of fine-grained, controls over the privacy of these models and kind of like what type of information they're sort of able to share. Okay, so to test the ability of the current models to kind of, have these more kind of fine-grained privacy controls, we've built this benchmark where we're sort of basically telling the model to kind of not reveal certain types of information. So this is just sort of like, hypothetically, we might want the model to not answer any questions about Italian citizens, right? And so then if you ask the model, who's the wife of this Italian soccer player, it should sort of, refuse to answer, basically. And so we have these kind of textual QA questions where we're trying to, get it to not answer certain types of questions. And then also, like information seeking visual question answering as well. So for example, if you have a photo like this and you ask the model to geolocate it, it should refuse. And so we're basically repurposing some existing QA data sets, including, pop QA, trivia QA, and then InfoSeek is a data set that my PhD student Yang created during an internship at Google, and he's sort of repurposing it for this kind of benchmark as well. Yeah, so anyway, so like, these kind of geolocation questions you shouldn't answer, but then there's other kinds of similar questions about like the architectural style of a church that would be sort of safe to answer. Okay, and this is basically the kind of baseline approach that we're kind of presenting in this paper to kind of test out the ability of different models to selectively protect different types of information. So you can see here we have some prompt, and we basically tell the model, don't answer questions about Italian citizens. This isn't the actual prompt we're using. It's much more complicated, but this is, what'll fit on a slide and is sort of readable, right? And then one thing that we found, though, is that we can actually get the models to kind of, in some cases, be kind of much more protective about privacy if we just sort of repeatedly ask it, are you sure? And then after kind of doing this a number of times, it actually sort of increases the privacy protections, right? So this is just sort of showing performance after like multiple steps of this sort of, iterative authorization. And at least for some of the models, it's sort of improving performance. Yeah, this is still sort of work in progress. So we may need to kind of, see if we can kind of get it to work a bit better with some of the open source models. So.
Did you try asking directly to give a confidence instead, like on the scale from 1 to 10? How sure are you or something like that?
That's a good question. Yeah, we didn't try doing that, but that's a good idea. Yeah, maybe we should do that as sort of a comparison, like a baseline or something. And so, yeah, so if you compare this to like model editing approaches like Rome, where they're actually kind of finding, like parameters in the model that actually encode this information and then trying to update it to like remove facts. It's this kind of approach, I think, is a little bit more scalable, right? Because yeah, when you start kind of making changes to the parameters of the model, everything just sort of breaks down after a certain number of edits, right? So like there's sort of more recent methods like Mehmet and stuff like that that try to scale up the number of edits you can make, but I still think it's sort of an issue is like there's some fixed number of edits, whereas like if you're like, okay, just don't answer any questions, any of these specific type of questions, you can kind of cover a lot more information out there.
You can actually you don't need the model to report the score. You have open source models, so you can actually just have a yes or no score. Can you use those?
Mm. You mean, so just look at the actual logits, you mean? Or? Yeah, that's a good question. Yeah, we didn't try doing that, but I think that would be a good idea to look at, yeah. I think so the main contribution in this paper is really like the benchmark, and then I think you could certainly come up with like all kinds of ideas how to better protect privacy, but
what's privacy score? Should it be 1? Is it?
Yeah, so it's the harmonic mean of essentially the kind of the performance of the model on the kind of protected data. So you want that to be high. So that's kind of like the utility. And then you have like a measure of privacy, which is basically like the F1, like QA F1 score on the protected set. So you want that to be sort of low, if that makes sense. So it's sort of taking both privacy and utility into account. Okay, so anyway, so this sort of works to some extent, but it turns out it's actually pretty easy to kind of get around this. So this is just one example of a kind of attack that we found was pretty successful on this type of approach. So here you can see it, this is basically asking the model to identify this person who's like a member of the Japanese House of Representatives in a situation where, you're not supposed to answer any questions about Japanese citizens. But if you basically just kind of, alter the image to kind of render some text at the bottom that sort of, has some misleading information about this person, then you can actually get it to answer. And we found a lot of other ways this is like pretty easy to break. So this certainly shouldn't be used in any kind of, sensitive application with the current models. And there's other kind of major problems here around like bias, right? So like different people from, some groups that aren't kind of the majority within a country or something like that might not get as good of protection as others, right? So kind of the main takeaway is that, the current models can selectively protect information to some extent, but their protections are like biased and they're not adversarially robust. But we're hoping that this benchmark can be sort of a step towards models that can do better. Okay, so yeah, just to kind of summarize the main sort of takeaways from the talk. So I talked about this work on sort of these trade-offs between computation and annotation, both in the case of domain adaptive pre-training and knowledge distillation. I also talked about this new work on schema-driven information extraction, where we're extracting data from tables, where the only source of supervision is like a database schema we provide to kind of to the model, and this sort of makes these models works well across lots of different domains and data formats. And then finally, I talked about this, so again, also sort of recent work in progress on, more fine-grained privacy controls and large language models. And yeah, thanks for coming to the talk. And yeah, I'm happy to take any more questions. I guess there was already a bunch of questions, but yeah.
About your first work, I'm curious how you think about data annotation versus compute trade-off nowadays with sort of this like instruction tuning type of data. It feels like task stuff, but also it's not really being done specifically for a task. It's not quite training because it's task like how do you think about how should we think about this intermediate data training layer now?
Yeah, that's a great question. So, I mean, I do think that this trade-off still comes up in like training these models, right? So like, I think like Llama 2, I mean, I think they did do a significant amount of data annotation there. It's like, I think for like the supervised fine tuning, it's like something like 27,000 demonstrations. And then I think they had like 1 million, comparisons for like the reinforcement learning with human feedback or something like that. So yeah, I haven't really done the calculation to like figure out how much that costs and how much that would sort of compare to like the compute cost for training Llama 2 chat, But I do think the trade-off comes up. I mean, I think people are evaluating this to some extent. So I think in the paper they mentioned like after they did a certain number of annotations that started to plateau, right? But I do feel like it would be nice to have like more transparency about like the costs of training these models and just allow people to do more kind of like meta studies on kind of like the costs of training models and the costs of annotation and just come up with better guidelines on how to like spend money for doing this kind of thing, right? I guess the thing I kind of worry about is like maybe there's some kind of not very efficient decisions being made, like maybe people are like, oh, let's just throw a ton of money into computation and where you could sort of achieve something similar, without that potentially. I mean, I think like you're saying though, I mean, the chat models can do some pretty impressive things that seem to be like not possible just only with data annotation, right? So it's, and you can sort of reuse them for lots of things, right? So it's, there's some kind of a, yeah, you get some benefit from kind of reusing the models. You don't have to like retrain them for every new task. That certainly is something to take into account.
It's almost like you have a third axis now, which is like prompt engineering.
Yeah, sure.
How money should I spend on prompt engineering instead?
Yeah, that's a good point. Yeah. I guess, yeah, that does sort of cost some money. I guess like, yeah, GPT-4 is getting a little bit more expensive in terms of that. Yeah.
Another kind of related question. I mean, often with annotation projects, there's a whole bunch of work that involves coming up with the annotation guidelines, right? And maybe training annotators and things like that. And there's a substantial amount of iteration. There's probably also, right, some setup cost for the domain adaptive pre-training and stuff too. I guess, how do you think about those other like hidden costs?
No, that's a great question. So that was sort of the assumption we made is that we're not taking kind of like the software engineers' time into account in these, or like the NLP engineers' time and account into these sort of calculations. I guess we sort of assumed the costs would be maybe similar between sort of like collecting all the pre-training data and kind of babysitting the models as they're training and tuning hyperparameters versus like you're saying, sort of like designing annotation guidelines and managing workers and things like that. Yeah, I think it's a good point though. Those are certainly like large costs that we're not taking into account in this analysis.
Although ideally, you want some of that annotated data for evaluation anyway, and then in that sense, that overhead is baked into any approach if you want proper evaluation data.
That's a great point. Yeah, I think that's a good point. Yeah.
You provide some interesting recommendations for the computation versus annotation. Do you have any sense of how those are changing over time, or could you extrapolate to, like given changing compute costs and value of annotation?
Yeah, that's a good question. Yeah, I mean, I feel like it's probably, I mean, certainly it's changing over time. I mean, there's lots of new models coming out all the time, like GPT-4 and GPT-4 Vision. They have all these new capabilities. And I think in some cases, they can actually do pretty well without really any annotation, like we sort of saw with the table extraction, right? Like this seems to be something that these models are just naturally really good at. I think in some sense, maybe because it's sort of almost like a code to code translation task, right? Like you have sort of like the LaTeX source code for the table, and then you're just trying to translate that into JSON. Maybe there's like enough data like this in the pre-training that it sort of like already has pretty good, pre-training data on sort of just translating between these different type of, code like data formats, So I do feel like it's very task dependent. Like I think for some tasks, the pre-training is just going to provide, much more useful supervision than others. So like the tasks we're looking at here are more these kind of like traditional NLP type tasks where you have like very specific annotation guidelines, like you're annotating spans or relations. So I think those are things where the large language models tend to not do as well with just instructions or few shot learning, because there's just like a lot of different choices you could make about exactly how you annotate the spans, right? And the model might have like a different idea than your annotators, like how to do it, right? So I think at least for these tasks where you really want the model to do something very specific that doesn't really align super well with the pre-training data, then the annotation is going to become much more important. Whereas if you have a task that's like more aligned with the pre-training data, then probably less so, But yeah, that's a great question.
All right, well, yeah, it's about noon, so if there are no other questions, let's thank the speaker again.